in one of the early videos, I gave you a sphere and I showed you how by varying the radius, how that would affect the volume of the sphere, and also by varying the radius, how that would affect the surface area of the sphere. Now, in this video, I want to know what happens when you vary the volume of the sphere, how that would affect the surface area of the sphere. So for example, let's say we've got a sphere of volume V. What happens when we double that volume? So it's now 2V. So when the volume is doubled, how would that affect the surface area of the sphere, and by how much? Okay, so basically we want to know the relationship between volume and the sphere. How by changing the volume, how would that affect the surface area of a sphere? Okay, so let's start by looking at this thing here and this thing here. So this is the formula for the volume and the formula for the surface area of the sphere. In one of the earlier videos, I showed you that when given this formula here, you can visualize it as this. You can visualize this thing here being in a bubble, and this thing here being in a bubble, and then you can actually say that volume equals some constant r to the power of 3. Okay. Now, if you don't understand this, you have to watch one of the earlier videos. And also when it comes to the surface area, you can visualize it as this. Now, because this bubble here is 4 is just a constant, pi is just a constant. It doesn't change. The only thing that we're varying is the radius. So you can actually say, so from here you can actually say surface area equals some constant r squared. Okay, so you can actually make. I've done 2 videos. One showing you this, how to get from here to here, and another video showing you how to get from here to here. Now, when you're here, you can actually say, oh, volume is proportional to the radius cubed, and here you can say the surface area is proportional to the radius squared. So when you plot a graph, of this volume and radius, it will look something like this. And then if you plot a graph of surface area and radius, it will look something like this. So this line here is in a form of something similar to y equals x squared, and this thing here is something similar to y equals x to the power of 3. Okay, so it gives you a rough idea. But now we want to investigate what happens when you vary the radius. When you vary the volume. So what happens when you vary the volume? How would that affect the surface area? Okay. So looking at this here, you well here well we want to know what happens when we vary the volume. Now I just have a gut feeling that it's the radius that connects the volume and the surface area. So I know I'm going to need to play around with the radius. So starting from this, I'm going to rearrange it to make r the subject, and then later I can put r into this thing here and see how it will affect the surface area. You will get an idea of what I'm talking about, as I will show you here. So starting here, let's rearrange this to make r the subject. So divide both sides by k. So v over k equals r to the power of 3. Now cube root both sides. So r equals the cube root of v over k. Okay. So now we've got so now we've got our radius. But this thing here, from my experience, because I've done this for a long time, I just have a feeling that it's better to work with indices. So remember, when you're given something like this, a over b, if you power it to a third. Now, if you don't understand this, watch the section on indices. Whenever you get power to a fraction, you can immediately visualize the cube root of A over B. Now here we've got this cube root. I'm working backwards now. I'm saying that V over K to the power of a third. Okay, so I, rather than visualizing, but rather than using this, I would rather use this. Okay, and now I can put it, so now looking at this thing here, I can actually put the R into here. Okay, so hang on. So currently we've got S equals K R squared. Now that I know R equals this, I can actually put it into here. Okay, so it will be this. S equals K, and then this thing here is going to be, I'm going to put the whole lot into the R here. So it would be R over K, and then a third here, and then the thing is we're going to square it. Okay, and by the way, this K is different from this K here, so let's call it K1, K2. But we don't really care about K. K is just some constant that we don't really care about. All that we know is that we are varying the volume. Okay, so now it looks quite ugly, so bear with me on this. So remember from indices, if you have something like this, x, and then you power it to y, then you basically just get x times y. You would times these two together. Okay, so in this case it would be this thing timesing this thing here. So this will become, hang on, K, I'm just going to call it K. I don't really care about K1, K2. I just know that they're just constants that we don't care about. So basically I'm going to merge these two together here. So it will become this, V over K. These two K's are different, but I don't really care. They're different, but I don't really care about them. So here it will be this. Okay, because by using this here from indices, we know that when you have something to the power of another thing, you just multiply the two together, so it becomes this. Okay, and from indices again, when you have something like this, let's say if you have something like this to the power of 3, it basically means A over B times A over B times A over B. So it's top times top times top, bottom times bottom. Well, basically, whatever this thing is here is going to be this, A to the power of whatever. Let's say in this case it's 3, B. So it would be this. Now I'm using the same technique here. Now, if you don't understand this bit, you got to watch the indices section. So here it would be this K, and then V 2 over 3 over K 2 over 3. Okay. So here again, I don't really care about this. I don't really care about this. But this thing is going to get multiplied to the top. So basically, it will be this K over K whatever here, and then time. I'm basically pulling this thing out. So it will be V 2 over 3. Okay, so here I've got a bubble here, multiplying another bubble here. Now this thing here, I don't really care. These are just constants. I don't really care about, because all that I'm varying is the volume. So remember, the surface area is this. All that I'm varying is the volume. I don't really care about these numbers here. So I'm just going to call this bubble. I'm just going to give this bubble a new name. I'm going to call it K. This K is different from this K and this K, but I don't really care. It's just some number that I don't care about. So let's just call it K. So the surface area is this. So from here you can actually say the surface area of a sphere is proportional to V to the power of 2 over 3. Okay, and this thing here from indices, you can visualize this thing as V to the third squared, or you can visualize it as V squared to the power of a third. And whenever you get to the power of a third, we don't really understand what it means to have a power of a third. So we are allowed to visualize it as a cube root. Okay, well basically, don't worry about this so much. Here you've got this thing here. So now what? Let me think. I can't remember. So we are here at the moment, and yeah. So the surface area varies by changing the volume here, and then what? Hang on. Let me think. Memory blank. Hang on. Um, um, then what? Memory blank. Okay, the volume here. Oh yeah. I know now. Sorry. So here we've got a surface. So here we've got a sphere here. Now we've got a relationship between volume and the surface area. So this is, let's say we have a sphere of volume V. So that would give us a surface area of this. Now what would happen if we double the volume? So now the new volume is 2V. Okay, so now our new volume is 2V. So let's put this into that V here, into this V here. Okay, so let's put it into here. Now so this is our old. Okay, now we want to look at a new situation where we doubled the volume. So the surface area will be some constant, and it will be 2. Our volume now is 2V to the power of. So this is for a sphere of volume V, and this thing here will be the surface area for a sphere of 2V. Okay, it's twice the volume. Now looking at this here, hang on. So here, remember from indices, when you have this here, let's say to the power of x, you can visualize this as 1 to the power of 1, and then it will be this times this, and then x times this here. So we can do this. Hang on. We can visualize 2 to the power of 1, v to the power of 1. So we can actually do this. So here k times 2 to the power of 2 over 3, and then times v to the power of 2 over 3. Okay. Now we need to write our new surface area in terms of the old surface area. Okay. So here this would be 2 to the power of 2 over 3, and then times k v. So basically you've got this here. So currently you've got this block times this block times this block. I'm just moving this block to the front. Okay, so this block here times this block here. So this is the surface area for our new volume. But the thing is, if you look at the old volume, look at this here. Old volume is given by this. This is our old volume here. Now look at this here. Down here, this is our old volume here. It's exactly the same. K v to the power of 2 over 3. But the thing is, our new surface area is this thing times the old thing. So if you jump to your calculator and work out 2 to the power of 2 over 3, hang on, calculator, 2 to the power of 2 to the power of 2 over 3, close it off, equals this, equals 1.8, sorry, 1.5, I'm going to round it off, 1.59. Okay, so it would be, so surface area equals 1.59 times the surface area of the old surface area here. So basically our new surface area will be this much times the old surface area. So when you double the volume of a sphere, so when you have a sphere and you double the volume, you basically times the old surface area by this much. Okay?